Okay, alright, so I'll move on to slide 3, and even before we do more stuff, here's something that I have to introduce to you. This is in our textbook also, it comes a bit later, but so far we are used to drawing our NMOS transistors and our PMOS transistors in this way, right, with an arrow. What you'll notice is for the NMOS the arrow went away. Then you may ask, okay, if I take the arrow out, how will I separate it from the PMOS, right? And so you see here on the right that the arrow that was inwards for the PMOS also goes away, but what we have done, or they have done, is put a little circle there. So these symbols, these new ones that I'm just showing you, they are also used quite commonly in logic circuits. Not so much when we do circuit analysis, but if we only are focusing on the logic aspects, then sometimes they'll drop the arrow and just go with this. So I need to show you that because that is it's a requirement to understand some of the other material. Okay, all right, with that out of the way, let's get into the real stuff here. Okay, so slide 4 is actually a review. It's a summary of everything that we studied so far in chapter 13 in the first 3 sections, 13.1, 13.2, 13.3. Okay, there's almost nothing new here. So I picked one drawing to show you the CMOS inverter with a NMOS transistor on the bottom and a PMOS transistor on the top. And this bottom one we call it the pull down, and the top one we call it the pull up. And also I'm showing the fact that transistors can be thought of as switches, right? A switch with a small resistance also, and a switch here with a small resistance. So particularly if you are interested in using the transistor purely as a on and off device, that means operation either cut off, or triode, meaning fully on, and not in the saturation region in the middle, then the switch representation is important to have in mind. Okay, there's also a small resistance in series because none of these devices can be on without and the current flowing without some resistance, right? We know there's a natural resistance, but if you ignore that for the moment, just think of this as a switch and this as a switch. Okay, and then I show on the input side that the input Vi can go high, in which case it brings a voltage value about VDD, or it can go low, in which case it brings a value of 0, right? And it can switch between high and low. So this stuff we know. This also we know, right? This is an inverter. This business of having a CMOS connected this way is basically so that when we have when we have a high on the input, the output goes low. The output comes out here, right, between the two gates, and that goes low. Similarly, when the input is low, the output should be high, and that is a basic inverter behavior, right? So we spent so much time learning about the inverter as implemented by a CMOS pair, two transistors paired together to achieve this result. Okay, so here I've written some words, let's quickly read those. The transistors are switches, right? When a transistor is on, the switch is considered closed, right? That's the basic understanding. Now the pull down NMOS transistor, this one, is on when the input is high, right? So when the input goes high, the NMOS transistor turns on, so this switch is closed, and the output becomes low, right? That's why we call it a pull down, because when the input is high, the output gets pulled down to 0. The output becomes a low. Similarly, the pull up transistor, the PMOS transistor, it's on when the input is low, right? Because naturally a PMOS transistor needs a negative voltage on its gate to source to turn on. So when a PMOS transistor turns on, a PMOS transistor is on when the input is low, and the input is low but the output gets pulled up high, right? It goes up as high as VDD. Hence it's called a pull-up transistor or a pull-up device, and the output becomes high. So all this stuff you should know by now. This stuff, the table on the right in the middle, is maybe new only because I'm putting it to you for the first time, but I'm sure, I hope, you guys have all studied logic circuits, Boolean algebra, and you know what a truth table is for a simple inverter, right? Input, output, V in, and this bar on the top is called V in bar, is also called the complement, right? So for an inverter, the truth table is when input is high, the output will be low. That's what the bar signifies, right? So I hope by now you know this. Now we have written this in terms of V, etc., but you can just say X and Y, right? And you can say the output is Y, the input is X. And so for an inverter, when X is high, Y will be low, and when X is low, Y will be high. Okay? Alright, so this is a summary. I hope this is quite familiar to all of you. And we move on. And here I introduce the idea of series and parallel switches. So all this material I'm covering is kind of introduction. We still haven't come to the first section in the chapter in the textbook. We'll get there, but I have about 10 to 12 slides even before we get there, because I wanted to make sure that you have the necessary background to understand what the chapter starts to talk about. And so rather than assuming you know all this, I thought, okay, let me spend some time writing this so that you have no excuse and you know exactly how to follow the material later. Okay. Alright, so series and parallel combination. If two transistor switches are in series, both have to be on for current to flow, right? So let's say we have two transistor switches. These are actually transistor switches, PMOS, active low. When the input is high, low, these turn on. So for VDD to come through this network and come out here at the bottom, they both have to be on, right? So that both A and B, so use the word AND, that means a series combination of switches, right? So AND means if two transistor switches are in series, both have to be on for current to flow or for the voltage to appear at the other end. Same here. If you want the ground to come up here, then both switches have to be on. A switch and B switch has to be on. What is an OR then? If two transistor switches are in parallel, like here or here, at least one switch needs to be on for the current to flow or for the voltage to appear at the other end, right? So I'm sure this is also not very new, but I thought I would refresh your memory about why series means AND function and parallel means OR function. Okay? All right. Okay, so now we are moving on to something really exciting, and this is logic table. It's a truth table, right? And the one thing I wanted to tell you is, as we study this chapter, rather than talk about OR function and the AND function, we talk more naturally about the NOR function and the NAND function, which is the opposite, the complement of OR and AND. Now once you have a NOR, you can always convert it to an OR, right? All you have to do is put it through another inverter, right? And then you get the opposite. So now that we have so many inverters, thousands, millions at our hands, in our hands, we are not scared of NOR or NAND, because all we do is use one more inverter and we have the OR. But much of the theory that we'll study is built around using NOR functions and NAND functions rather than OR function and the AND function. Okay, so just become comfortable with that. So what is a NOR function? What is a NOR truth table? Okay, so let's say we have an input at A and an input at B, let's call it VA and VB, you know this is an OR function, right? When you write VA plus VB, it's an OR function. So when this is low or this is low, the output is low. But when this is low or this is high, then the output goes high. So for an output to be high, either input A or input B has to be high. Here also the input A is high, hence the OR function, the output goes high. Of course, when both are high, you still satisfy the condition that one or the other should be high, and that is also high. With a NAND or an, so this is until OR, right? Now if you flip this, every one of these, if you put it through an inverter, that means you have that bar function, then the output becomes exactly the opposite of this, right? The complement of this. So when this is low, this goes high. When this is high, this goes low, and so on. So that's a NOR truth table. Similarly, let's look at a NAND truth table. And to understand a NAND, first let's understand a AND. Just A-N-D. What is an AND? When either in first input or, no, let me rephrase that. What is an AND? When the first input and the second input are both high, then the output is a high, right? So only one condition here gives you a high. Both this and this has to be high, then this is a high. So that's an AND function. Now what is an OR? No, sorry. So that's an AND function. Now what's a NAND function? That's the complement of an AND function. So you see, whenever this is low, this is shown as high because it's the complement. And when this is high, this is low. So that is how we define the NOR truth table and the NAND truth table. And you notice that the NAND output is high only one time out of 4, while here the NAND truth table, the NOR truth table is only high 1 times out of 4, while the NAND truth table is high 3 times out of 4. Okay, so that is one of the conclusions. Okay, I'm going to move on to slide 7, and here we spend some time understanding the NOR business, okay, the NOR truth table. So here we finally get back to drawing circuits with transistors. Now previously, if you look at slide 4 again, we just had 2 transistors and they take one input and give us the inverted output, right? Only one input, one output, and 2 transistors. Now on slide 7, we are dealing with 2 inputs, VA and VB, and we still have one output, and we want that output to be the NOR function. And so to do that, we need 4 transistors, 2 NMOS and 2 PMOS. And how should you connect them so that you can get exactly this truth table that we just studied, right? We want all this to be truthfully implemented or executed by this circuit, right? And so you can try various combinations, but this is the combination that works. Actually, there are many combinations that work, but for our purpose, we are going to study this particular method, okay? And we are only going to use PMOS and NMOS. Obviously, you can use BJTs, you can use diodes. A lot of things are possible, but for our education, and to follow what's in our textbook, this is what we'll study, okay? So, what I show you is, to execute an OR table, we have 2 NMOS transistors at the bottom, and they are connected in parallel. and we have two PMOS transistors on the top which are connected in series. And the way I show VA and VB, I hope you're familiar with it by now. VB, I have shown a red line also to help you understand. But VA is tied to NMOS 1 and PMOS 1. So you can see VA goes to the gate of PMOS 1 and NMOS 1. Similarly, VB goes to the gate of NMOS 2 and PMOS 2. So you can trace that. Okay. So I have written that here input VA is tied to NMOS 1 and PMOS 1. Input VB is tied to NMOS 2 and PMOS 2. So A is 1, B is 2. And this is the truth table that we are going to execute. So next slide, I pick a case, right? The topmost case where I show with the arrow, this is case 1. So we want to ensure that when this condition on the input is met, that indeed the output is this. And we'll go through 1, 2, 3, 4 for the NOR table, and then we'll do the same 1, 2, 3, 4 for the NAND table. Okay. So I walk you through each step, and I'll only do this for this one slide. I'm going to have to skip because I know we are always running short of time. But let's go through this one in detail so you understand how I write it. Okay. All right. So NOR case 1, meaning the top one, VA is low, right? And VB is low. That means both of them are 0. So what happens when VA is low? When VA is low, and remember VA is connected to NMOS 1 and PMOS 1, right? So a low on the gate of the PMOS 1 turns it on. You know that, right, by now? Similarly, a low on the NMOS 1 turns it off. So we have, because of this VA being low, PMOS 1 is on and NMOS 1 is off. Similarly, VB is low, right? What does that do? Same thing. The PMOS 2 turns on because PMOS likes a low input on its gate, turns itself on. The NMOS 2 doesn't like a low input, turns itself off. So this is what happens because of the VA and VB being low. So both NMOS parallel switches are off. So both these are off. Both PMOS series switches are on. So both these are on. So what happens? Since both PMOS series switches are on, since both these are on, the VDD comes down to the Vout. So VDD appears at Vout. Great, right? So we already got it. What we wanted, which is we want the Vout to be high according to the table, right? It is required. Now VA plus VB is low. That's the OR function, but we are not interested in the OR, we are interested in the NOR, which is this has to be flipped. That's high. And we achieved it. Can we stop our discussion here? No, because we know that two PMOS transistors alone are not enough. We spent a lot of time to understand why we always need NMOS and PMOS to be in pairs, right? They have to both exist together because there is no static power consumption. We don't need huge resistors in the drain circuits, right? To get all the benefits of CMOS, we always need to make sure that they exist together. So for every PMOS, there has to be an NMOS. So these have to exist, and we have to make sure that they cooperate with what's going on the top. Otherwise, your circuits are not going to work. So that means when this is on, the opposite transistor has to be off, and vice versa. If this is on, that has to be off, right? So let's check on that too. Now we already saw that they're both off, right? And more importantly, we have to check that if they're off, whatever state they're in, these two also, they don't bring some additional voltages, etc., to confuse the issue, to bring some new stuff that doesn't logically apply, right? So what should happen to these? If we want this to be out, these have to be off, so that there is no path for ground to suddenly show up there, right? So luckily, no path exists between Vout and ground, since both the NMOS switches are off. So now we are happy, right? We checked that these two are on, that brings the voltage here, VDD comes out to Vout, so Vout is high, and both the NMOS switches are off and they are in parallel, they're off, so it works. And Vout can stay safely at VDD, which is a high. Alright, I will do one more, and then I promise I'm not going to do many more because this is time consuming, but let's look at this quickly. Now we are in case 2 of the NOR table, right? Here, VA is low, but VB is high, right? So let's follow the logic and see what happens. So VA is low means PMOS 1 is again high and NMOS 1 is off, right? That's how a low on the VA makes them. Similarly, VB now is high, right? According to the truth table, VB is high. If VB is high, we know the PMOS it's attached to goes off. So VB is attached to PMOS 2, so PMOS 2 is off. And because VB is high, NMOS 2 turns on, right? So this is the summary of the conditions. So what do we have then? One parallel NMOS switch is on, this is on. One series PMOS switch is on, right? One of these is on, 2 is on. Sorry, 1 is on. So this is on and this is on, right? Okay. So let's now continue. Because only one of these is on, obviously this VDD cannot come down, right? Because PMOS 2 is off. If this is off, this voltage can come here, but it cannot come through to Vout, right? Because PMOS 2 is off. Great, so we conclude that this cannot be off, or this cannot be high. But we also want to make sure that it truly is at ground and not floating in some middle voltage, right? It would be perfect if we can also prove that ground has come up here. Then we can say, yes, Vout is off. So how do we ensure that? Because this is parallel, if at least one of these is on, if one of these two switches, if you consider them switches, if at least one of them is on, then this ground connects to Vout. And that's exactly what we know is true. Because NMOS 2 is on, that's what I say here, since NMOS 2 is on, it provides a path between Vout and ground. So Vout connects to ground. Hence Vout will equal ground, which is low. Okay? So this is the way to go through each step at a time and understand that this circuit perfectly gives us the execution of the NOR function. Okay? So I've got case 3, case 4. You should check the logic and make sure you understand it. Then I introduce the AND function. For an AND function, the connection is slightly reversed. The two NMOSs are in series, the two PMOSs are in parallel. We still have VA and VB, the same connection. Input VA is tied to 1 and 1, VB is tied to 2 and 2, the red one, that's VB connection. And the truth table is here. Remember, for an AND function, both A and B have to be high for the output to be high. That's an AND. Then if you flip it to get a NAND, you put the bar on it and show this to be a low. So this is the circuit and the same 4 cases, case 1, case 2, case 3, case 4, you can follow the logic and you will see that this connection with the two NMOSs in series at the bottom and the two PMOSs in parallel at the top will perfectly execute this logic. Okay? So this understanding, and I call this CMOS NAND here, NAND, this understanding of these 8 slides is very important. Some of you, I'm sure, find it easy. Some may find it a little difficult, but I request you to go through each one and totally get it in your mind so that we don't have confusion as we move on to some of the more advanced stuff in the chapter. Okay? All right. Now I move on to actually the first, the material in the textbook. And even this slide actually is not in the textbook yet. But this is a summary of some important rules from Boolean algebra. And I hope you folks have studied De Morgan's laws, which tell you what this is. So all this is also important background information. And then in the next slide, slide 18, is when I begin the actual material from the textbook. But let's spend another minute here on slide 17 to understand the background. So here all I'm saying is, we know that if B equals A bar, then B bar equals A. So they can be flipped around. Here's some basic rules of algebra. Some of it we may use, some we may not use, but they're all important to revise. So you know what A plus A equals A, right? This is probably the only type of arithmetic in the world where this is true. You add two things and you still get the same thing, right? Similarly, A or 1 is always 1. A and 1 is always A, etc. So take some time, become familiar with these. 11, 12, for example, are important. Then there's De Morgan's laws on this side. What it says is, it's called the rule of the complements, right? If you take the complement of an AND, that equals the OR function of the complements. Similarly, if you want the complement of an OR, that's the AND of the complements, right? I hope you're familiar with this. Become familiar again if required. All right, so we finally move into 13.4.1 from the textbook. And here we start looking at seriously at some of these circuits and trying to understand how they behave. Okay. So first sentence. So we show on the circuit, we have this on the top, pull-up network. These are generally PMOS. And then we have the pull-up network on the bottom. Generally, so far we have seen maybe 1 or 2 transistors, right? NMOS at the bottom, and that's the pull-down combination. And PMOS on the top, that's the pull-up combination. You can have 1, 2, 3, 10, however many on the top, but you must have an equal number on the bottom. That's the way they work in the CMOS world, right? Okay. So instead of calling them PMOS pull-up transistor, now we call it pull-up network. A network having 3 transistors, or 4 or 5. So the PDN and the PUN each utilizes devices in parallel to form an OR function and devices in series to form an AND function, right? So whenever you have something in series, it's an AND. If they are in parallel, it's an OR. Also, all input combinations that call for a high output. So when Y has to go high, it will cause the PUN to conduct, and the PUN will then pull the output node up to VDD. So if the inputs are low, the output will be pulled up to VDD by the pull-up network. Same way the PDN will conduct for all input combinations that require a low output. There may be many things here, but bottom line is we want that Y to become low, then this will work. This will function, this will turn on, and it will pull the output node down to 0. Okay? All right, let's move on. Slide 19 is from the textbook. He shows us some examples of pull-down networks. So you have a parallel combination a series combination. Now these we have already seen, but maybe we haven't yet seen this, which is a parallel series combination, series parallel combination, right? There are two in series and the two are together in parallel. So it's a lot like understanding resistances in series and parallel, same thing. But obviously we are talking about transistor switches now. So this is a PD or pull down network consisting of NMOS devices. This is important when the output has to be low, and this is the way to write the logic function, right? The y is a plus b or a or b flipped, complemented, right? That's why it's a low. Okay, so follow this logic and try to become familiar. I'm sure this is not difficult either. It's BC in series, so you put the AND function. Together they are in parallel with the A, which hence you put the OR sign in the middle. Same thing here, but we are talking about the pull-up side now. Okay, so pull-up networks, PMOS devices, output is high. Parallel, series, series parallel. Here's an important rule that we use a lot in the textbook, and so I will read it out to you. To obtain the PUN, we should write y in terms of the complemented variables. Now we already did some work with the NOR and the NAND. I showed you an actual NOR and NAND using two PMOS and two NMOS devices, and we were able to easily understand why we need a series and why we need a parallel, right? It wasn't so difficult. But as you get into more complex functions, logic functions, like for example this is somewhat complex. This is easy, we've already done this. This is easy, we have already done this. But if you get this, how do you go about creating this, right? Sometimes it's easy, but it can become difficult. So now in the textbook, we start to develop some rules that we follow, so that automatically, mechanically, we are able to create these networks, series parallel, without having to guess. Okay? And so to develop those rules, here's one important first rule. To obtain the PUN, right, the pull-up network, that means this top portion, we should write y in terms of the complemented variables. So what does that mean? You'll see that as you go ahead, go forward. Here, you notice that the equation is written in terms of the complements, right? Here we write the equation, the previous slide now, okay, when we are looking at the pull-down networks. In the pull-down networks, the equation we have written is in the straight terms for A, B and C, not complemented, but just by themselves, A, B, C. But if you look at the next slide, slide 20, all of them are flipped. And this is still valid, right? If you use De Morgan's laws, any function, any logical function in certain variables, you can write them in terms of the complement. And so the rule is, if you're trying to create the pull-up network, the top portion, you have to first write the same logic equation in terms of the complemented variables. Okay? So that's a rule. Alright. Now the same two input NOR gate, which we know very well now. I know we can write this with our eyes closed. But let's follow the rules in the textbook to write it. Okay? And see if that makes it easier or more, difficult. So what is the logic of a NOR gate? You know this, y is to be low, that means the output must be low. The PDN is conducting, right? This is conducting, so that this goes low. When A is high or B is high, right? Then you get the NOR function. We saw the truth table for it. So that is written as y equals A or B with a bar. Now this you can write using De Morgan's first law as A bar B bar. You know this also. So keep this in mind. Now let's actually create, let's say this wasn't given, right? Take this out. If this wasn't given, can you create it using these equations, right? So can you create so you always start by creating the PDN, the lower portion, that means the output low. So use the first part of the equation, right? This part, right? When you say first part, this part, that is y equals a plus b bar, or y bar equals a plus b. Remember, this side has to be without complements. Then we say, we know a is high or b is high. So the PDN is a parallel combination of two NMOS devices, right? We can conclude that because we know OR means parallel. And the type of devices, right? The type of devices that goes on when the input is high is the NMOS. It can't be the PMOS, right? The PMOS only goes on when the input is low. Okay. So let's look at the bottom now to find the PUN. That means the output has to be high. To do this, you have to use the second part of the equation, this part. And so I show the second part here. Now you work with y equals a bar b bar. When does y become high? According to this equation, when a must be low and b must be low, right? Then you will get y to be a high, right? So that is the only logic that satisfies it, that you want a y to be high when the inputs are low. So when a is low and b is low, the flip of them will both be high, and so the output is happy because both the inputs are high, or both the variables have taken the high after flipping, and so a must be low and b must be low, and then this y will be high. And we are implementing an AND function, so we have two series PMOS devices, right? So if this was not given, this is how you use the rules that we just developed to write this. Now you can write it with common sense like we did, but if we didn't have that and we had to write it using the rules, this is how the rules work. Okay? Alright. Same thing with the two input NAND gate. Same rules, right? First you say what is the logic? The logic is that y is to be low when both a and b are high. I don't need both two times. So y is to be low when both a and b are high. And that is the truth, the logic table. So y is written as this, or y is written as this using De Morgan's laws. Now same thing, take this out and create in your mind or by yourself the logic circuit diagram. So first you find the PDN, which is when the output is low. You go through the logic and you come up with PDN is a series combination of two NMOS devices. Then you say, okay, now I got this, I'm happy, I'm going to get my high, right? But I really need to know how to write the top portion to find the high. This is when its output is low, this is when the output is high, right? So how do I do that? I use the second part of the equation, which is from here. So what does this equation say? The output will be high when the input A is low or the input B is low, because then these are flipped, the lows become the highs, and either this or that will give me my high output. So either A is low or B is low is what is going to give me that. And we know that the only type of device that likes it when the input is low is a PMOS device. It turns on. So the PUN consists of two, and because we have the OR, two parallel PMOS devices. Okay? So I hope you can follow this logic and understand it, because we are going to use this quite a bit. Okay, I have a lot of material to cover. I will try and stop this at 50 minutes. I have one more recording just to do a few problems. So I may do some of the theory also there in part B, but let's keep moving. So I'm on slide 23, sorry. Now we looked at what we already know, which is the NOR and the NAND. But let's say we have to build a logic circuit like this. Now this is not a simple NOR and a NAND, right? This is a complex. We can write a truth table. I'm sure you guys know how to do it. But we don't even have to worry about writing a truth table. We can actually directly execute the circuit. Okay? But to be able to do that, you need to do a little bit of Boolean algebra. So in this case, and this is an example in the textbook, all the details are there. I have 3 slides on this example, but it's many pages in the textbook. Please read it so that you become comfortable. But let me walk you through this and then we can stop this recording. So y equals a times b plus cd. That means a and b or c and d, right? That's the way to read that, with a complement on top. So can you simplify this? Why are you trying to simplify this? We can write the PDN using just this, right? We know that. But to write a PUN, we want this function to look like this, where you only have the complements of all the variables. A has to be complement, B has to be complement, C has to be complement, D has to be complement. If you can write it in that way, then you are a very happy person, because then you can easily create the PDN like I show, the PUN as I show in the previous slide, by using only the complements, right? So back on slide 23, then what we have to do is spend some time and energy to go from this to this. Okay, what are the steps? Now remember, I want to also say this is not always possible. It's possible sometimes. Most cases it's not possible, and we can still create logic circuits. We have some examples later on even though you can't break it down so nicely, you can still, but it just becomes a more complex circuit. But for now, let's focus on just this and going to completely complemented variables. Okay, so y equals a into b plus cd. So applying De Morgan's laws, that multiplication is split into, is replaced with an or an addition. But now you are flipping both these functions, right? Then you take this, the b plus cd, and convert it into an AND by putting the bars on individuals. Then you take the cd inside and create it and convert it into this is a AND, you create it into an OR. And you can't simplify it anymore without losing the bars. And so since you are interested in the bars, this is what it becomes. Okay? Now we can see how to create the bottom portion, the PDN, and the top portion, the PUN, for this particular function. So use the first part of the equation, y equals a, b plus cd, or you can just move this bar over, y bar equals a, b plus cd. How do you read that? What it means is y will be a low on this side when a and this whole thing are both high, right? because this is an AND function. So when A and all this are both high, then Y should be a high and Y bar should be a low, which is what you're interested in. You want to make the output low. So how do you implement this function, right? So start with the one inside, the smallest, the deeply nested brackets, right? Deep inside bracket, C and D. So there's an AND function, that means they have to be in series, so draw the AND. Then you have a B which is in parallel with this because there is an OR, so draw the B and CD in parallel. Now to all this you have a which is in series because it's an AND, so then you draw that. So this whole thing is implementing this complex function and you get a Y that is low when all these A, B, C, D are high. Okay, so that's how you implement this. So the PDN is a combination of 4 NMOS devices. Next, you have to execute the top portion. Follow the same logic. The top portion is like this. So start with the one in the middle. This is C or D low, right? So C or D. Begin with that. Then we have A, no, A low or B low, right? B low and, right? So B low and gives you a series of B low with this stuff. Then finally coming out a little bit, A low or all of this low. And so for A to be low in parallel with all of this, it comes out like this in parallel. So the PUN is a combination of 4 PMOS devices because only the PMOSs work when A's and B and C and D are low. Okay? Now you put it all together and you have this full circuit. And you have, because you have A, B, C, D, 4 inputs, 4 variables, you need 4 transistors on the top, 4 on the bottom for a total of 8 transistors to implement this function. Okay? So that's how you implement a complex gate, and I think I'll stop here because we are running out of time and I'll continue when I come back in my next recording.